All right, so in 4.8, what we're going to do is look at another kind of proof. It's called the coordinate proof. A coordinate proof is basically using algebra and geometry to write a proof. So it's not going to be as formal as a two-column backing everything up with a reason. It's going to be more like using your formulas, like distance formula, slope formula, Pythagorean theorem, maybe formulas for area, which is what we're going to look at today, that we learned back in chapter 1. But you're going to place a shape on a coordinate plane, and then you're going to try to prove something about those shapes that you've placed on the coordinate plane. So the first part of the notes are going to be pretty easy. We're just going to be talking about how should you put your shape on the coordinate plane, and then we'll look at one proof together in 4.8. And then 4.9 today is really just two theorems and their converses. And it's not about writing proofs today on 4.9. It is just simply, here's a picture. Can you apply the theorem to find a missing angle measure or a missing side length? So it's pretty easy in 4.9. Okay, 4.8. So, like I said, a coordinate proof is a style of proof that just uses coordinate geometry and algebra. But the very first step in a coordinate proof is to position your shape in the coordinate plane. Thank you, Naomi. Welcome, Reese. Can you get through? Yes, you do. Hang tight for just a minute, guys. What you don't have is the review for the test. And I told them you'll have all day in class on Tuesday to work on this. We'll review also on Thursday. And then we won't test until the following Monday, okay? But I wanted to get it in your hands in case you wanted to start working on this weekend because it's pretty long, okay? And you'll need some graph paper, so make sure you have graph paper. This you can keep, this you can keep, and this I need back, but you can get your sticker off of it, okay? All right, and Reese, we just got started on 4.8, okay? Do you need a chair for your leg? Are you sure? I can put one like right here beside you. Okay, you let me know if you're not, okay? All right, so like I said, the first step in writing a coordinate proof is to place your shape on the coordinate plane. And they're going to be pretty picky about how you should place that shape. So these are the 4 strategies you're going to use when you decide where should you place your shape. Basically, the first strategy is you want to try to keep all your coordinates positive. You don't want to try to do a proof with a bunch of negative numbers. And so the best way to keep all your points positive is to use the origin as one of your vertices and keep the figure in the first quadrant. Okay, if you'll keep it in the first quadrant, which remember it's quadrant 1, 2, as you go counterclockwise, 3, 4. You want to keep your shape in that upper right-hand first quadrant if at all possible, because then that will keep your coordinates all positive, okay? The next 3 options, those are if you can't put it in the first quadrant centered at the origin. So some other options could be, second one, you could center your figure at the origin. So the way that would look is maybe you have a square and you want to make the center of your square the origin. That's going to be...
Hey, John, please call the office. Hey, John, please call the office.
That's going to be a little less helpful, but it might be helpful in the sense that you're going right and left the same distance, you're going up and down the same distance. So it would keep your coordinates all the same numbers, just some positive and some negative. Okay, but again, really this first one is the one we're going to focus on the most. Keep it in the first quadrant, use the origin as your vertex. Another option would be you could center one side of your shape at the origin, so maybe you would place your shape like this so that it's centered, one side of it is centered on the origin. Again, a little less helpful, but there might be reasons that it's placed that way. And then the last way is to use one or both axes as sides of your figure. Now this one you have to be super careful about. If you use both axes as a side, meaning that you place your shape like this, so that you're using both the x-axis and the y-axis as a side, what does that mean you have to have in your shape? A right angle. So you could use that if it's a right triangle, if it's a square, if it's a rectangle, but if you're not confident that you have a right angle, then you can't do that, okay? So these are the strategies, and then we're just going to look at some examples, and we'll start off really easy with numbers, and then we're going to stretch it a little bit and use some variables. Okay, so it says position a square with a side length of 6 in the coordinate plane. So again, you should have a graph, right, on your notes? Okay. So you're going to place a square with side lengths of 6, and you want to always try to use that first strategy if at all possible. Keep it in the first quadrant. Use the origin as one of your vertices. So if I start here, what directions and how far would I need to go to create my square? Okay, right 6 and also up 6. Remember to use graph paper. Do not create your own graphs like I'm doing a bad job of modeling for you. Make sure you grab that graph paper behind you when you leave. So then we would just create our square. We're going to go right 6 this direction and up 6 this direction to create our square. The key here, though, is not just that you can graph it, but I will be looking to see, can you label all of your vertice points? Okay, that's what I'm really checking for, is did you graph it correctly, and did you label all of your vertice points correctly? So what would we label this point? 0, 0. What would we label this point to the right? So x first, then y, so what is it again? 6, 0. What is this point up here on the y-axis? Careful, this one right here. 0, 6, because we're not going left or right at all, so 0 and then up 6. What's the final vertex over here in the far right? 6, 6, because we're going 6 to the right and 6 up. Is everybody okay with that idea? Okay. So that one's pretty easy, just placing it in the coordinate plane and labeling your coordinates. The next one's also going to be pretty easy, because again, we're just dealing with numbers. So if you flip it over, it says position a right triangle with leg lengths of 2 and 4 units in the coordinate plane. So what kind of shape do we have? Right triangle. So if it's a right triangle, what can we do to get that right angle? What are we going to use to make our right angle? Both of our sides are going to go on our x-axis and our y-axis, right? And we want one of our legs to be 2 and one to be 4. Does it matter which one is which? It doesn't matter. They don't tell us, so it doesn't matter. So do you guys want to go up 2 or up 4? Okay, I heard up 2 first, so I'm going to go up 2. If we go up 2, what do we have to do to the right? 4 to the right. And then we're just going to create that right triangle that's made by those 2 legs and our hypotenuse. And then you have to label the vertices. Again, I want to emphasize that's the big part that I'm checking for. Can you label your vertices correctly? So what is this point going to be here? 0, 0. That one should be easy. And then up on the y-axis, what is that point? 0, 2. And then on the x-axis, 4, 0. Any questions if it's just numbers? Okay, so now we're going to look at some where they're changing it to variables. Okay, I'm going to come back to this. This is not in your notes, but this is what you're going to see on your test and on the review. So we're going to come back to this and we're going to add it into your notes. So I'm going to skip this for a minute and come over to here. So position each figure in the coordinate plane and give the coordinates of each vertex. Notice what happens now. We're dealing with what shape? Rectangle. But what do they tell us about the rectangle? The width is what? M. And the length is what? Twice the width. So if the width is M and the length is twice the width, what would we call the length? 2M. Is everybody with me there? Okay, what I have found is what is usually easier for students is if they think about this first without putting it on the coordinate plane. So I'm going to draw just a rectangle over here and label the sides of my rectangle before I put it on the coordinate plane. So we want the width to be M and we want the length to be 2M, right? But now we want to place this shape on a coordinate plane and label all the vertice points. We do not have numbers for those vertice points. We don't know what M is. But what we're going to have to do is make up a value for M just so that when we place our rectangle on the coordinate plane, we are doing it so that it is drawn correctly, so that the width is half the length or the length is twice the width. So you're just going to make up a number you want for M. Doesn't matter. Somebody give me a number, but not too big. 3, okay? Keep in mind, M is not 3. We're just going to pretend it's 3 so that we can get our figure drawn to scale, where the width is half the length or the length is twice the width. So we're going to go up 3 on our graph to get our width. What is our length going to have to be then? 6, twice that. So then we're going to go right 6. And we're going to draw that rectangle. But when we label our coordinates, we are not labeling them 3 and 6. We are labeling them with the values that they gave us, M and 2M. So these are the things that you're going to be using when you name your coordinates. So keep in mind, you went right to M, you went up M. You just pretended M was 3 so that you could get that drawn correctly. Does that make sense? Okay, somebody else may pick M as 2 and their shape is going to look different, but their coordinates are still going to be the same as yours. So this one should be easy. What are we going to label the one at the origin? 0, 0. And now what are we going to label the one on the x-axis? How far did we go to the right? But we pretended that. That's not really what our value was. What is the length of this side? 2M. So what am I going to label this point? 2M, 0. Okay, so you're going to use the variables to label your coordinates, not the numbers that you make up. Just make up a number so that you can draw it to scale on your graph. But then after that, pretend there are no numbers again and go back to your variables. Okay, how about on the y-axis? How far did we go up? Okay, we went up M, so it's going to be correct, Alex, 0, M. And then what is that going to make this point over here in the far right? Careful, we went right how far? 2M, but we went up how far? M. So it should be 2M, M. Is that making sense? Questions? Okay, so to me that's the hardest part of this, is just making sure you can do it with the variables. Other than that, it should be pretty easy. Let's try another one. So read that for a second and then tell me what shape we have. So what shape are we dealing with here? A right triangle. So again, think about it without going on a graph first. We're going to draw a right triangle. One leg needs to be what length? S. And another leg needs to be T. Are those letters the same letter? No. So what should that mean about your two legs? They should be two different lengths. You get to make up whatever lengths you want them to be on your graph, but make them different. So what do you guys want? How far do you want to go for S? 4. Okay, I'm going to go right 4. Put a point. What do you want to use for T? 7. So I'm going to go up 7. And then I'm going to draw that right triangle. Just keep in mind we are not using 4 and 7 when we label our coordinates. We just made up those numbers so that we could draw a right triangle that had different leg lengths. When we name our coordinates, we're still using the letters S and T for our distances that we went right and up. So what is the coordinate here on the origin? 0, 0. That one's easy. What about on the x-axis? S, 0. And then on the y-axis? 0, t. Could I have switched my s and t? So you could have had T0 and 0S, and it would still be correct. You get to choose which leg you want to call which letter. Questions? Okay. So what I want to do now is go back. I'm going to skip some of the examples in here because that's really all there is to this, is can you place it on the coordinate plane, put the coordinates on there. But I want to go back and I want us to look at a proof that I did not put in your notes. So I want you to take a minute. Maybe use, let's go to the back here, on the back of the notes, far right-hand corner, scratch out the directions that are there and write these directions down. Okay, so I'm going to give you a couple minutes to write this down. So we're going to write a coordinate proof, given this, prove this, and you can use the graph you have right here on the right. But scratch out the directions and write down these directions so you have a good example to look back at. Once you get it all written down, go ahead and graph the rectangle ABCD on your graph and draw in the diagonals, because the letter E is supposed to be the letter where those diagonals intersect. So this is going to be the letter E. Okay? So graph that rectangle. If you don't have room on your graph, just make it bigger or maybe change your origin. Okay. How many people need more time to copy it down? All right. A little bit longer. I'm going to go too fast. Okay, so graph your rectangle, draw in your diagonals. This is an example of a coordinate proof. And again, notice we put the rectangle in the first quadrant so that all of those points would be positive. So we want to prove the area of triangle ABE is 1/4 the area of the rectangle ABCD. So this is going to take you back to chapter 1 and your area formulas. How do I find the area of a rectangle? Heard somebody say it. What is it? Length times width. Okay, how do we find the area of a triangle? Okay, so, and they usually don't call it length and width for a triangle, but same kind of idea. It's called 1/2 what? Base and height. Okay, but you are correct. You're going to multiply those and take a half because that triangle is basically half of a rectangle, right? Everybody with me on our formulas? If you don't remember those formulas, write them down. You need to go back and study those from chapter 1. So now what we're going to do is just use our coordinate graph to figure out those distances. That's the coordinate proof, putting it on a coordinate plane. Okay, so let's start with the rectangle. The nice thing with this one is we don't have to use distance formula because everything that we need is either vertical or horizontal, and we can just count it. What is the length of our rectangle? If you count this distance right here, what is the length of your rectangle? 4. Okay, what's the width of the rectangle? 10. So we are just going to write our formula down. Remember that this is a proof, so it's all about showing your work. You don't want to just put 4 and 10. You want to make sure that you are describing what 4 and 10 go to. Let's do this. So make sure you put area of the rectangle is length times width, and then plug in your units. 4 times 10. And so what is the area of the rectangle? 40. Okay, then you're going to go show your work on how to find the area of the triangle. We're looking at ABE. Which triangle is that? Top, right, left, bottom. Bottom triangle, right? ABE. So we need the base of the triangle and we need the height of the triangle. What's the base of the triangle? 4. So we have 1/2 times 4. What's the height of the triangle? Okay, careful. It's actually 5, right? If we go all the way over to here, that's 5, because this would be our height of our triangle. Height goes from your vertex straight down to your base. So the height would be 5. What is half of 4 times 5? 10, right? It's half of 20, which is 10. So then you're going to show that 10 is 1/4 of 40. It says prove the area of the triangle is 1/4 the area of the rectangle. So you're going to write that down and show that. You found the two areas, so now you're going to write down the area of the triangle needs to be 1/4, the area of the rectangle. That's what this says, right? Area of the triangle is supposed to be 1/4 the area of the rectangle. So just write it down and then plug in your units and show that it's true. What's the area of the triangle? Careful, triangle. 10. What's the area of the rectangle? 40. What is 1/4 of 40? 10. So then we have 10 equals 10, and that proves that the triangle is 1/4 the area of the rectangle. Is this making sense? It's not a 2-column proof. It is just putting it on a coordinate plane and then showing your work to prove what you're trying to prove. The kicker is, for me, make sure you don't just put 4 times 10 is 40, 1/2 of 4 times 5 is 10, and then say 1/4 of 40 is 10. You didn't name or identify anything you were talking about. So make sure you're labeling. What are you finding? Area of the rectangle, area of the triangle. What are you trying to prove? And then show your work underneath. Any questions? Okay, that's 4-8. Yes, sir. I'm sorry, say it again. You just have to rewrite, yes, rewrite what it's telling you to prove in terms of an equation. Okay, just like I did there. You don't have to write it all out in words. Just what are you trying to prove here? That this triangle is 1/4 the area of that rectangle, and then show that math. Okay. All right. Let's look at 4-9. And like I told you, 4-9 is just 2 theorems. So you should get some time to work on homework today. We'll see how far we can get before our play people leave.
Part of the interruption. There's those Beta Club students that are going to help with the Civitan soup sampler today. Please dismiss the Beta Club students that are going to the Civitan soup sampler today. Thank you.
Okay, so this section is going to focus on two specific kinds of triangles, an isosceles triangle and an equilateral triangle. What do we know about isosceles triangles? Okay, they have at least two congruent sides. What do we know about equilateral triangles? All the sides are equal. Okay, so we're going to look at two theorems that apply to those two kinds of triangles, and then we're going to solve some problems. These are our last four vocab words. And again, your vocab test will not be until Thursday, and so Tuesday we'll do the practice review like we always do. And there's 29 words this time, so it's kind of big vocab test. Okay, it says recall that an isosceles triangle has at least two sides congruent. Then now let's make sure you understand some vocabulary about isosceles triangles. The two congruent sides are called the legs. So the definition for leg is the congruent sides of an isosceles triangle. The ones that are congruent are called the legs. When the legs meet, they come together, they form an angle. That angle has a special name. It's called the vertex angle. So where the two congruent sides connect, that angle, number 3, would be your vertex angle. The side that is not necessarily congruent, the side that's across from the vertex angle, is called the base. So that's your next definition. The side opposite the vertex angle is called the base. And because that side is called the base, the other two angles, which are made by the base, angle 1 and angle 2, they both share the side that's the base. Those angles are called base angles. So this is a base angle, and this is a base angle. The base angles are the two angles that have the base as a side. Okay, so just to make sure you really understand that vocabulary, I'm going to draw a triangle right here. Which angle is the vertex angle? E. Which legs, or which sides are the legs of the triangle? E, F, and G, E, G, or G, E, either way. Which side is the base? F, G, and what are the base angles? F and G, okay? So that vocabulary is really important for the theorems that we're going to look at. So here's the first theorem, and again, I told you it's really just a couple of theorems and their converses. So the first theorem is called the isosceles triangle theorem. The name of it tells you what you had to know to start with. It's isosceles triangle theorem. So what that means is they're going to give you a picture of an isosceles triangle. You're going to know that the two sides are congruent. This theorem says if the two sides are congruent, then the base angles are congruent. The base angles, remember, are the angles not in between the two congruent sides. They're the ones across from the two congruent sides, angles B and C. So your base angles will be congruent if it's isosceles. Those are the ones across from the congruent sides, not the vertex angle. So in this picture, which angles would be congruent? Say it again. F and G. So if it's isosceles, the isosceles triangle theorem says the base angles will be congruent. Does that make sense? Okay, the converse just switches, right? So the converse of the isosceles triangle theorem does not show us an isosceles triangle by legs being congruent. Instead, it's going to show us that the base angles are congruent. If the base angles are congruent, going the other direction, that means the legs are going to be congruent. Okay, so in this picture, those are the sides across from the congruent angles. So that's DE and DF. So I'll draw another picture up here. ABC. And this time, If these two angles are congruent, which two sides must be congruent? BC and AC, or CA. These two. Okay, not the one that's in between the two angles, but the other two sides across from them. Okay, that's this theorem. Any questions on isosceles triangle theorem or its converse? Okay, I'm going to skip the first example. We'll come back to it because I want to get to some actual problems before people go into the play leave. So here's an example that you'll see. First thing you're going to have to ask yourself is, what kind of triangle do you have here based on the markings? Okay, it's isosceles. And what did we just learn? If this is isosceles, what should be true? Okay, so I'm hearing the same thing from several of you. Angles D and F should be congruent by the isosceles triangle theorem. They told us it was isosceles based on the markings. Now we know the angles are congruent. Okay, they want us to find the measure of angle F. We're going to have to use things we've learned before and what we just learned today. What could we do here to find F? Exactly. We know all three of them should add to be 180, so we'll just take 180 and subtract 22. What does that leave us with? 158. And then if we know the last two angles together have to be 158, what would we do to find each one? Just divide by 2 because they're the same measure, right? So 158 divided by 2, 2 goes into 15 how many times? 7. 7 times 2 is 14. Subtract, we get 1. Bring down our 8. 2 goes into 18. 9 times. 9 times 2 is 18. Subtract, we get 0. So that means it's 79 degrees for angle F. Pretty easy? Okay. If you look at the next one right beside it, this time what are they giving you true in the picture? Or what kind of triangle is it in the picture? Okay, so it's still isosceles. So using the same theorem, isosceles triangle theorem, which angle should be congruent? G and J. Okay, again, it's the ones across from the congruent sides, not the one in between them. That's your vertex angle. So that means this should be the same as this, right? So we're just going to set them equal and solve. So x plus 44. Yes, sir. You do not unless it asks you which theorem. So in this case, it's just saying find the measure. You can just find the measure. I just feel like we remember it better if I keep bringing it up. So x plus 44 equals 3x. From here, what would we do? Subtract x. So 44 equals 2x. And then what? Divide by 2. So what is x? 22. Is that our answer? No, they want us to plug it back in and find g. So if we plug it back in, what is 22 plus 44? 66. And don't forget your degree symbol. Don't forget your little m for measure. Are we good? All right, we have one more theorem. So hoping I can get to it before you guys have to leave, so you get the big idea anyway. So the next two theorems, they don't call it the equilateral triangle theorem and its converse. They call it the equilateral triangle theorem and then the equiangular triangle theorem. And basically the name tells you what they're giving you to start with. So if it's an equilateral triangle theorem, then they're starting with a picture that is equilateral. And this theorem says if a triangle is equilateral, it will also be equiangular, which means every angle in the triangle will be congruent, right? And what did we decide in a previous lesson that each of those angles will be then? What measure? 60. Because remember, if you take 180 and divide it by 3, what do you get? 60. So if it's equilateral, you can now say it's equiangular, and now you can say that means every angle is 60 degrees. Equilateral triangle theorem. If it's equilateral, it's also equiangular. And then the other theorem is just the converse of it. They're just going to switch it. But instead of calling it the converse, they call it the equiangular triangle theorem. Because when you look at the picture, what are they giving you? Bless you. They're giving you an equiangular triangle, right? So the name tells you what's given, and then it just goes backwards. If it's equiangular, then it is also equilateral. So now what do we know is true? All the sides are the same, right? So if it's equiangular, it's equilateral. If it's equilateral, it's equiangular. This is only true for triangles. Okay, only for triangles. So if you look at the next two problems, last two on the back here, says find the value of x. So first of all, what kind of triangle do you have? Equilateral. And we just learned if it's equilateral, it is also equiangular. And then we said if it's equiangular, what does that make every single angle? 60 degrees. So that means this 2x plus 32 is equal to what value? 60 degrees. So then you can just write that equation. 2x plus 32 equals 60 degrees. And then solve. So we would subtract 32. So 2x equals 28. Divide by 2. What is x? 14. And that's all they asked you to find, right? Okay. If you look at the next one, what kind of triangle do they give you on the next one? Equiangular. But if it's equiangular, we know it is also what? Equilateral. So it's just going backwards there using the equiangular triangle theorem. So now we know all three sides are equal. So what could we write down to solve for y? Same thing, Chris? Is that what you're going to say? Yes, we can set those two sides equal to each other, right? Because we know all three are the same. We just need 2 to set equal to each other. So 5y minus 6 has to be the same as 4y plus 12. And then from there, we're going to solve. So what do you want to do? Add 6. So 5y equals 4y plus 18. And then what? Subtract the 4y. And 5y minus 4y is just y. So y is equal to 18. And that's all they asked us to find. All right. So that's really the big idea. We skipped the first example, but I think I'm just going to skip it. And if you need help, if you have something like that on your homework, I'll help you. And I'm going to give you the rest of the time today to work on your assignment. If you're going to the play,